So I'm kind of the. It's not very well.
No. I feel honestly no yeah, I mean I've heard of it because my research professor next in when I wrote
Yeah. Molly, do minds the beginning? Yeah, so the chemistry part of it is it comes from the areas, but I study a variety of technologies. Trying to develop
All right, welcome everyone. Okay, welcome everyone. We're going to get started for our very last public talk of 2023. So my name is Hannah Fernberg. I'm a PhD student here at the Trottier Space Institute and also your moderator this evening. So tonight we're going to be learning all about the physics surrounding this year's Nobel Prize. And before we get started, I just have a few reminders. So first, I'm just going to throw up our code of conduct for this event. So I'll just give everyone a second to read that. All right, so if anyone has any questions this evening, scientific or otherwise, you can email us at tsioutreach@physics.mcgill.ca and we'll be happy to answer your questions, although I think scientific questions Brad will be able to answer. So this year's Nobel Prize in physics was awarded to Pierre Agostini, Ferenc, Krausz, and Lillier for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And this ultra-short timescale physics allows us to understand the behavior of the smallest particles experiencing short-lived interactions. So it's my pleasure to welcome tonight's speaker, Professor Brad Siwick, who is a professor of both physics and chemistry here at McGill. And his lab works on developing new techniques that allow complex and short-lived structures and materials to be determined at the atomic level. So his work and his group's work is in this field of short timescale physics, and that physics was at the heart of this year's Nobel Prize. So Brad is a true expert and is going to teach us all about why we should care about this science. So after the talk, we'll have a Q&A period. So we'll have plenty of opportunities to ask all of your most pressing questions to our speaker tonight. And for anyone joining us live on YouTube, hello, and feel free to just type your questions in the chat. So without any further delay, Professor Brad Siwick.
All right, so what do you think? Can I do this without the mic at the back? Is that everything all right? Yeah? All right, because I mean, you can see my state, right? Like if I tie myself down with this microphone cord, it could get ugly. Somebody in the back is gonna have to save me from myself. Well, okay, so it's a real pleasure, so I should be sharing my screen.
Yes, and it is, it's sharing the presenter mode for some reason. Maybe reshare. Versus PowerPoint, but I think it's really. Okay, so it's sharing properly on the Zoom. Would you like me to
So
put this close here?
have totally different set of.
And then now if you reshare, I think it should. Okay.
Okay, great. Yeah, we tried this before, of course, but so okay, it's a real pleasure to be here. Thanks to everyone for coming. Thanks for the invitation and the introduction. It would have been I think cool to hold this a little bit closer to the date of the announcements, but the term sort of had other ideas for me. Was quite busy, so it's a real pleasure to be here to talk to you and unpack some of what you sort of read in this announcement here for the 2023 Nobel Prize in Physics, awarded to, as we just heard, Pierre Agostini, Ferenc Krausz, and Anne Lullier for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And so what I'm hoping to do with my talk today is unpack all of that. Yeah. So I've pitched my talk at the level of an interested layperson. Okay. So I hope I don't. Well, anyway, I think that's going to be the right level for this crowd. I'm going to try, and at least my plan was to provide you with everything that you really need to know in order to really, at a perfectly reasonable level, understand what's going on in the physics associated with this Nobel Prize. Okay, so before I go on, I want to mention that those were the Nobel laureates this year, but the year before, in 2022, there was an award made for the same physics, right? Attosecond science, okay, for pioneering contributions to ultrafast laser science and attosecond physics. And the laureates there were slightly different. And they were slightly different. Okay, so Anne is here and Ferenc is here, but Pierre Agostini was replaced with Paul Corkum, and this matters to me because Paul Corkum was one of my mentors in Canadian science. So it's a little bit disappointing to all of us in Canada that this giant of Canadian science didn't quite sort of well, he won the Wolf Prize last year, but was not awarded the Nobel Prize with the other two this year. And what's important, okay, that's a fact, but important going forward is when I'm unpacking all of that stuff that I talked about, you're going to hear and see the important contribution that Paul Corkum and his lab made to this whole story. Okay, so there's many scientific actors involved, and I'm hoping to, through my talk, be able to sort of outline each of their special contributions to the development of this field over, I think, a span of about 15 to 20 years. So the stuff that I'm going to cover today. Okay, so I'm going to start by setting the scene. Okay, I'm going to provide you with the relevant context and a little bit on background. Okay, so like every good physicist, I'm going to start providing this context. Okay, because the prize was given for attosecond science. I'm going to situate you sort of on a timeline. Okay, these are not all, but a set of very relevant time scales, okay, that relate to physical phenomena of different kinds, right? So on this timeline, at the one extreme end, you know, is the age of the universe, right? So, which is interestingly, you know, something on the order, close enough, to 10 to the 18 seconds old, right? So, okay, so we come down here to another time scale, the time scale on which you and I live most of our lives, right? So the time between heartbeats, which is 1 second, right? So you've got 18, you know, 10 to the 18 heartbeats in sort of the universe, right? But now let's go and I think inside of this room, sort of many of the same people have heard plenty of talks about phenomena sort of that relate to these kinds of timescales, cosmology, and these interesting subjects, right? So at the other end of this timeline, right, is what we're going to talk about here today, right? So rather than 10 to the 18 seconds, we're going to be talking about phenomena that occur on timescales on 10 to the minus 18 seconds, right? So that's 32 orders of magnitude away, right? So, and interestingly, 1 second is to the age of the universe, pardon me, an attosecond is to 1 second as 1 second is to the age of the universe, right? So it's just so these are amazingly, almost inconceivable sort of short periods of time that we're talking about here. Okay, but there is a range of phenomena, importantly. So this is, okay, so it's exotic in the sense that the time is very short, right? But important for this discussion is that those time scales are the ones that control most of the phenomena that you live and touch, okay? So I'm going to describe this to you. So this time scale, this range of time scales between 10 to the minus, let's say 13 seconds, okay, or 10 to the minus 15 seconds, which is a femtosecond, by the way. Oh, the joke I was supposed to start with. I was just reminded of it. Okay, so as you're going to see as I go forward, because I worked in a little bit my own work here. So I wanted to make the joke that I'm only 3 orders of magnitude away from the Nobel Prize. Okay, so you're going to see this is my particular playground. I play sort of in this area, sort of on time scales of femtoseconds, because those are the ones that are relevant to chemical reactions and phenomena that occur in materials. Okay, so and 3 orders of magnitude down from there is this attosecond time scale, which we've just learned. Okay, but I'll justify sort of in upcoming slides, is related to the time scale on which electrons themselves can reorganize. Okay, so matter, atoms, molecules, solids, right, are made up of either simple or complicated arrangements of atoms. Those atoms are joined together because they share electrons in some way, right? And as I'll show you, right? So the properties of those molecules and materials emerge because of a complicated dance between sort of the nuclei and the electrons. Okay, the electrons control sort of a lot of this dance as we're going to see going forward. Okay, so what I'm going to focus in on this timeline, okay, is a set of physical phenomena that take place. Pardon me, a set of physical phenomena and the tools that we as scientists have developed, okay, that allow us to study phenomena on these what appear like amazingly short timescales. Okay, so and I've already sort of foreshadowed this. Okay, So I'll ask the first question. What is the time scale on which, or pardon me, what is the ultimate time scale upon which atoms can move inside of you and me and the stuff that surrounds us, right? So, okay, it takes some time, but not very much, okay? So if you think of an atomic rearrangement, there's a bunch that you could think of, right? One kind of atomic rearrangement would be a chemical reaction, right? So a chemical reaction where certain chemical bonds, right, are unmade and new chemical bonds are then reformed, okay? This requires kind of an interchange of electrons and potentially sort of the rearrangement of atoms inside of a molecule, right? As you go from the reactant state of the molecule to the product state, you rearrange atoms. How fast or what is the typical time scale on which that rearrangement occurs? And the answer is about 10 to the minus 13 seconds. Chemical bonds are made and broken typically on this time scale, which is not to say that chemistry happens on that time scale. I'm talking about the molecular physics. I'm talking the time scale on which a chemical or a bond can be said to be either made or broken, okay? That takes about 100 femtoseconds. And this is actually a really easy number to figure out, right? So you should understand why this is. One of the things you should leave this room with is an understanding of why this is the fundamental time scale. So when I knock on this table, right? So what is the speed at which the disturbance, okay, I induce in the upper layer propagates into the material? What do you call that speed? It's the speed of sound, right? So the speed of sound in most materials is a number of about 1,000 meters per second, right? Okay, and I think this is a sophisticated crew, right? And so what's the distances between atoms inside of molecules and materials?
10 to the minus 10.
10 to the minus 10, and that's known as an angstrom, right? So if the information, right, propagates through the material, right, at the speed of sound, 1,000 meters per second, okay, and motion only needs to occur sort of on the angstrom level to make or break chemical bonds, because those are the interatomic separations that we're talking about, right? So like distance equals velocity times time tells you, right, that the time scale at which that motion takes place, right, is about 100 femtoseconds, right? That's it. So, you know, and there's other things that are not chemical making or breaking of bonds, but vibrations of atoms inside of molecules and materials, right? At room temperature, the atoms are always jiggling and wiggling, right? Atoms are jiggling and wiggling, and they can execute a complete vibration as far away as from, so they're normally in one position, but they can execute these kind of vibrations that take them away from their average position and back again. And that time, going away from their average position and back again, okay, can't proceed any faster than about 10 femtoseconds. Those are the fastest, those are the strongest, the highest speed vibrations inside of any of the materials that which we know, okay? So chemical bonds are breaking on a 100 femtosecond time scale. The fastest vibrations of atoms inside of solid matter, 10 femtoseconds. So this leads you to the following important concept or idea, right? That all motion that takes place inside of matter, atomic matter, so all motion that takes place inside of molecules and materials is frozen if you can make an observation in less than 10 to the minus 15 of a second, right? If I can go look into matter, okay, and my microscope or whatever I'm using, right, allows me to make a measurement sort of in a time that's only 10 to the minus 15 of a second, okay? There is no atomic motion at all. The nuclear coordinates, like the positions of the atoms, is fixed in space, right? So, which sounds like a silly thing to say, because Professor Siwick, there's no chance in heck that you're ever going to make a measurement in 10 to the 15 of a second, right? Right? There's just no way, right? But it turns out that's not true, okay? So 1 femtosecond is 10 to the minus 15 of a second. That is 1/millionth of a billionth of a second, okay? That's a really blazingly short amount of time. But what's the tool? Okay, what tool do we have that has the possibility of accessing this time scale? And the answer to that is light. Okay, light gives us the means by which we can make such measurements. Okay, why does it do that? Well, okay, light is an electromagnetic wave. I think most of you will know this. Okay, that is, it's a self-sustaining oscillation of the electric and magnetic field that has the configuration that I've shown here for a wave propagating to the right. Okay, so the electric field oscillates along in this picture, the x-axis, and the magnetic field oscillates in this picture along the y-axis, orthogonal, 90 degrees. Okay, but they're in phase with one another. Okay, this between sort of this zero crossing in the oscillation and this zero crossing is a number called the wavelength, right, for that wave. Okay, that's how long the wave is. Okay, and you know that there's an entire electromagnetic spectrum, right? There are there's short wavelength light and long wavelength light. There's radio waves and there are gamma rays, right? So, and there's a whole bunch of stuff in between. Okay, visible light is somewhere between 700 and 300 nanometers, the wavelength, right? And important to note, if your wavelength is 1 micron, so a little bit to the red of your vision, okay, the period of the wave, okay, the time it takes, if you're a little observer, imagine you're a little observer sitting here that's capable of measuring the ups and downs of this electric field, the time it takes to observe the electric field going up and down, sort of one cycle once, is only 3 femtoseconds for 1 micron light, right? So this electric field goes up and down in 3 femtoseconds. This is the tool. This is the tool that gives us access to sort of the all of that phenomena that I talked about before, okay? But it doesn't do so out of the box. You need to be very clever, right? And not only do you have to be very clever, you have to stand on the shoulders of people who are also very clever, and they stand on the shoulders of people who are very clever also, right? And this, you get enough of these people standing on each other's shoulders and you can invent something like the femtosecond laser. Okay, so the femtosecond laser is a remarkable development over 20 plus years, right, that allows you to produce not continuous waves of electromagnetic radiation, but instead short pulses. And when I say short pulses, I mean really short pulses. I mean pulses of light that are only 1 oscillation of the electromagnetic field. Okay? In this space, that's 3 femtoseconds. Up, down, that's it. Right? So amazing. Okay? And these are now technology. Anyone in this room can go buy one. Yeah. So, and well, if you don't want to go buy one yourself, you just have to pay your taxes, and then Professor Siwick can buy one, and then he can invite you to his lab, and he can show you this amazing thing that you bought for me. Okay, so us, because we share our science with everybody, of course, right? So all right. So, and I guess just go, bouncing from one Nobel Prize to another, I'll just mention that a Canadian played a huge role in the development of that femtosecond laser technology I just mentioned. Donna Strickland, okay, currently a professor at the University of Waterloo, was one of the Nobel laureates in 2018, not so long ago, right, for the development of key technology inside of one of those femtosecond lasers. Okay, so the ability to produce unbelievably short bursts of laser light. Okay, so what does that get you? Now, you do all that hard work and you produce femtosecond laser pulses. And I've tried to give you a little bit of a heads up that oh, I think I'm muted. So I'm worried that the people online are muted.
It's muted. It's going through the app.
All right. Okay, so I think I've given you a little bit of heads up here, right, about what you can expect to see, right? So everything that happens, right, in oh, what's happened? I'm frozen.
That's it, business.
It does. Let me actually kill my.
Nice.
Sorry, everybody. I think we'll get it quick.
Thank you, Chris. Things are moving.
Right. You see, like we were like existing in a femtosecond there, right? So all atomic motion was frozen. So this is what you can see. You can look at the inner life of materials, okay? Liquids, solids, molecular complexes. This molecular complex up here that you're seeing actually is a photosynthetic light harvesting complex. So a simple one, not the one in green plants, but one in other plants. Okay, and what we can learn by using these femtosecond laser tools is the way these molecules harvest light, direct the electronic excitation energy into a usable way, right? We can actually follow the way water molecules interact, vibrate, hydrogen bonds, maybe some of you know about those, are made and broken. You can follow the vibrations of atoms inside of liquids and the formation of ice. You can study all of this complicated dance, as I say, between the nuclear positions and the surrounding electrons in real time using femtosecond laser pulses. Okay, this is really important because, as Richard Feynman said, everything that living things do can be understood in terms of the jigglings and wigglings of atoms. And so if you follow those in real time, you can actually make a movie, okay, of the way a protein functions, right? So what are the nature of the atomic rearrangements that give that protein its function? Okay, the architecture you can sometimes see, you've taken a chemistry course or something, or a biochemistry course, and you see these pictures of proteins. This is the way the protein looks, right? Okay, if the protein was so frozen, okay, and didn't fluctuate and wasn't dynamic in its structure, it almost certainly wouldn't work, right? So it's these fluctuations that give most proteins structure. And the same thing is true for materials, okay? So here's a rogues gallery of a few of my favorites. This is a lithium ion battery material, right? And the lithium ions are shown in red, and they need to intercalate in between these sheets, right? That's a dynamical process. They get in there. How do they get in there? Because of fluctuations. This here is the current very exciting photovoltaic material, right? So light harvesting, okay, artificial light harvesting is mostly sort of done by silicon, like panels, right? But this is a new material that does a really excellent job and should be cheaper, okay? And it harvests light by absorbing light and then separating charges and moving them to other places. And that is entirely because of the way these octahedral cages fluctuate following the absorption of light, okay? Here's another material. This is one I've studied a lot. It's a material that sort of changes its properties dramatically, sort of as temperature changes by 1 or 2 degrees. It goes from being an insulator to being a metal. And this is a really interesting material, a high temperature superconductor. So it has zero resistance below about 100 Kelvin. And all of these properties emerge because of this dance that I talked about, right? This complicated interplay of the particular arrangement of the nuclear positions, the atomic type, and the way the electrons interact and are shared, right? The architecture of materials is dynamic. Okay, and now we're sort of building up some ideas and we're getting into the direction of attoscience, okay? So what's happening there? Electrons are the glue that binds these atoms together inside of materials or molecules. But more than that, they're also the director of the atomic structure. They tell the atoms where they need to be in order to have a stable solid. And they also determine sort of the nature of transformations between one structure and another, and whether certain motions happen with large amplitude or certain motions happen with small amplitude. The electrons are the key, okay? At my level of interest, okay, I can make a good approximation. And that approximation is called the Born-Oppenheimer approximation. And just so you know, yes, that Oppenheimer. Yeah. Yeah. So before he was building nuclear bombs, he did something maybe even more amazing, which was to lay the theoretical foundation for most of what I do. And it was just to notice that electrons are really light. Yeah. So, you know, the electron weighs about 1/1837 the mass of a single proton. Okay. So the single electron that orbits a hydrogen nucleus, right, is much lighter than the proton. Therefore, it can move much faster than nuclei. Okay. This fact means that for any particular arrangement of nuclei inside of a molecule or inside of a material, it's possible to make the reasonable assumption that the electrons are always arranged specifically, sort of in the following the laws of quantum mechanics, right? Are arranged specifically, okay, so that they're in their lowest possible energy, always. Okay, they can always figure out how to arrange themselves so that their energy is lowest. Okay, which means that the nuclei, as they move, okay, they move on a surface like a potential energy surface. Okay, so they're told which way is a bad way to move and where they should move back entirely because of the electron energy and how it changes as the nuclear positions change. Okay, nuclear positions change slow. The electrons are constantly rearranging to make sure that they're in the lowest energy configuration. The nuclei move. Maybe that raises the energy a little bit, and the electrons say, go back to where you were, right? That's kind of how it is. So this is what I mean by they're the director of molecular atomic structure, its transformation, and its motions, right? Okay, so where do I plug in? Okay, I develop tools in order to watch that, right? And I combine femtosecond lasers, electron microscopes in order to make molecular movies of just these kinds of processes that we talked about. I don't buy my electron microscopes, but I do, as I said, buy my femtosecond lasers. My electron microscopes are made in-house, and one of the people in the audience has helped me, Eamon, build these things. Okay, so that's all I want to say about it. Okay, so this is my playground. I'm playing on the femtosecond timescale, looking at the motions of atoms inside of molecules. Okay, so and you can do that with femtosecond time resolution. You can actually make movies of atomic scale processes in molecules and materials at that level of resolution, because what I just told you, right, that at timescales below 10 to the minus 15 seconds, atoms aren't moving. The nuclear positions are fixed in space. Right? So, well, what would it take to resolve that electron business, right? Okay, as I said, the electrons are always rearranging to make sure they're in their lowest energy, right? If I wanted to, instead of looking at the atoms, I wanted to look at how the electrons are behaving, what would I need? Okay, the dynamics that underlie that Born-Oppenheimer approximation. Well, what would you need? Okay, let's just do a little thought experiment. Let's consider a hydrogen atom. Okay, so this is a very bad picture of a hydrogen atom, but it's the only one I could find that showed things orbiting. So that's why I'm showing it to you. Okay, so this is the hydrogen atom, and you might ask, not really. Okay, the question is, how far away from the nucleus? Okay, first of all, a hydrogen atom only has one proton in the middle, and it only has one electron around the outside, right? So let's consider the electron in a hydrogen atom rotating around this purple, right? So the radius at which, okay, the electron orbits the nucleus in a hydrogen atom is called the Bohr radius. It's 0.53 angstroms. close, right? The classical speed of the electron as it orbits around that nucleus seems really big, right? It's let's call it almost 8 million kilometers per hour. Okay, so the electron orbits, okay, at 8 million kilometers an hour. Okay, the distance it is from the nucleus is really small, right? You know, half an angstrom. Okay, so okay, just compare this. The speed of an F1 car, sort of on the islands in the summer, is 300 kilometers an hour. It's got nothing on electrons orbiting a hydrogen atom. So what's the time required for an electron to go around the nucleus once? Okay, the answer is 152 attoseconds. Okay, single orbit, right? So the Earth orbits the sun once per year, right? That's 3 times 10 to the 7 seconds. So there's a lot of orders of magnitude difference between the time it takes for an electron to go around the nucleus of a hydrogen atom once compared to the time it takes for us to orbit the sun once, right? Okay, so fast, right? Attoseconds, the time scale of electron dynamics inside of matter. Okay, there's another way to think about this. So what's the speed of light? Okay, the speed of light is, you know, roughly 1 billion kilometers per hour, okay, or more common number, 3 times 10 to the 8 meters per second, right? So ask the question, how far does light travel in 1 attosecond? So, and the answer is surprising, 3 angstroms, right? Everyone thinks of light as the fastest thing there is, right? So it is the fastest thing there is, right? But even light can only travel the distance between atoms inside of molecules and materials in 1 attosecond, right? So, and this is actually an important thing. This is a general idea that applies here. So as you go to shorter and shorter time scales, the distance scales also go down. Okay, fast things happen small. Okay, slow things happen big, which is kind of it's an important idea. Okay, so now that's the background. Okay, this is kind of, I think I've tried to give you some context, and I've kind of tried to cite the whole thing. And now what I want to do is give you an intermezzo on a few fundamental concepts in quantum mechanics, only what you need to understand the attosecond physics. Okay, so the first thing is matter waves. And this is quite amazing. So we are literally, it's the 100th year anniversary of this idea. So which we owe to Louis de Broglie. Okay, he submitted his thesis in 1924, and the core idea in his thesis was, maybe massive particles, okay, like an electron, an atom, or an elephant, okay, have wave-like properties the same as light, right? And he made that quantitative. He said maybe the wavelength of a massive particle is related to the momentum of the particle in the same way as was previously determined for light. No equations, I'm not going to show you any, right? But this is the idea, okay? And so what does that mean for an electron, okay? So it means that the wavelength, electrons have a wavelength. It's not a bullet, okay? It behaves like a wave. And the wavelength of that depends on the speed or the voltage with which it's been accelerated, okay? And this is the important axis here, okay? These wavelengths are very small, okay? They're definitely smaller than the interatomic separations, okay? And they're way smaller than the wavelength of light, invisible wavelengths, right? These are, if these were light waves, these would be X-rays, okay? So that's important going forward, okay? So quantum mechanical idea number 1, all of the things that you thought of as particles actually have wave-like properties, okay? And so what do I mean? What wave-like properties are you talking about, Professor Siwick? Well, one of the things that waves do is that they interfere with one another, okay? Waves can interfere with one another, okay? That is, the crests of waves can add constructively and increase in amplitude, but a wave crest can add with a wave minimum and zero out. Destructive interference. Constructive interference and destructive interference. You're seeing this mesmerizing video of two sources of waves and how the waves that they emit interfere as you move away from the sources. Okay, that's a simulation, but look, you can do that yourself in the summer. Do what this guy is doing, grab a couple of things, pound on the surface of the water, you can produce exactly the same pattern, right? Waves, okay? An important wave-like phenomena is interference, okay? Constructive or destructive, okay? And a great way to look at wave interference is by using something called the double slit experiment, where you have a source of waves incident on a screen that has two holes, okay? And then the little wavelets that go through these two holes then go towards a screen, and you look at the interference pattern on that screen, okay? And if this was light, you know, to see an interference pattern here wouldn't surprise you because you know light is a wave. I've just showed you some pictures and some videos, right? Waves interfere, yeah, right? But what about this? What if I do the same experiment, okay? The same experiment, but instead of having light incident on two slits, I have a beam of electrons. And that beam of electrons is incident on those two slits. And then I look at the pattern of electrons that show up on this detector screen, okay? And the first thing I'm going to do is block one of the two slits and see what I see, okay? And then I'm going to block the other slit and see what I see. And if I do that, okay, you see exactly what you would have expected, right? If I block one of the slits, I just get a blob, right? The electrons that go through kind of give me a blob over here, right? The electrons that go through this slit give me a blob over here. And so if I look on the detector, that's just what I see, a smear, a blob, okay? But now I'm going to unblock both of the slits, okay? What are you going to see? Ah! Right? An interference pattern. Okay, this is data, by the way. This is a real measurement. This is not this is real life, right? So this is a real measurement. Okay, you can see places where the electrons appear to be constructively interfering and places where they've destructively interfered. You see no electrons here. Okay, and okay, this is the best part. Okay, so this is the video. If I can show it. Darn it. I think I have to go ahead rather than screw around with this. I'll show who's interested the video afterwards. Because it really is very interesting. This video was taken at a very low electron current. 1 electron going through this whole instrument every second. Yeah? Only 1 every second. And so you need to measure lots of electrons before you see this interference pattern form, right? And if I showed you the video, you could see that you end up with this grainy 1 electron at a time image, okay? Building up to have this interference pattern sort of by the time you count 100 million electrons, right? So it's remarkable. But the key concepts are these. Okay, so clearly electrons have wave-like properties. Okay, they are described by something called a wave function. Okay, where parts of this wave function overlap, electrons can interfere with themselves, right? So, and that's the important part. An individual, well, that's one of the important parts. An individual electron can only interfere with itself. 2 electrons don't interfere with each other. Okay, electron interference comes from the wave function that describes 1 electron interfering with itself. This is an important idea that we're going to build on for this attosecond stuff. Okay, the other important quantum mechanical concept that we need going forward is something called tunneling. Okay, so if an electron was really a particle, right? And it was on a potential energy surface, right? So how else can I describe that? So it would roll like a ball, right? So the electron might have enough energy to roll halfway up the hill, and then it would roll back. The only way the electron, if it was really a particle, could get to the other side of this hill and be found over here is if it had enough energy to go up to the top of the hill and carry over, right? But the electron is not a particle, it is a wave. And it does wave-like things, not particle-like things when it sees a barrier, okay? And wave-like things mean that part of the wave can leak through the barrier and be found on the other side. Light does this all the time, right? So you can have a thin mirror, light will leak through and appear on the other side. So there's if you have light coming to a surface and reflecting back in, part of the light wave sort of makes it through into the other medium. Waves do this, okay? So here's a simulation. So this is a wave function, maybe for an electron, incident on a wall, and you can see quantum mechanics, okay, gives you this tunneling process. Part of the electron wave that should reflect completely off of this wall, if it was a particle, leaks through the wall and appears on the other side. This is called quantum mechanical tunneling. It is one of the most striking consequences of quantum mechanics. There are instruments designed in research labs that make use of this phenomena only. They're called scanning tunneling microscopes. That was also a Nobel Prize. So electrons are wave-like. They interfere with themselves and can tunnel through barriers. These are the things that you need in order to understand attosecond science. They need one additional thing to make the surprises complete, okay? You need to consider, what does the light look like, okay, when you take an atomic vapor and you heat it up, okay? So you know, people who are old enough to have seen neon signs, okay? There's a lot of young people who've probably never seen a neon sign, right? So people who have seen neon signs know that if you have an atomic vapor contained in a tube and you put a current through it, it glows. It gives off light, okay? Electric discharge tube. If you take the light given off by an atomic vapor, okay, and you put it through an instrument called a spectrometer that allows you to measure how much light comes out at what wavelength, you see something surprising when you look at the emission from electric discharge tube of an atomic vapor. Rather than a full rainbow like this, you see what is called line emission. Okay, there is light at specific wavelengths, but nothing in between, right? So this was one of the most important observations at the early part of the 20th century for the development of quantum mechanics for the first, okay? That when they looked at the light given off by these sort of gas discharge lamps, that you saw line emission rather than continuous emission spectrum. And the reason that you see this line emission is because electrons inside of the gas are bound to the nucleus. And bound electrons, it turns out, from quantum mechanics, can only occupy discrete states. Those discrete states have different energies. So when you have an electron in an atom, it can be in one state or another and have one energy or another, but it can't have anything in between those energies. So there are only discrete states that are allowed for bound electrons in atoms, and you can make transitions between these energies, okay? You can make transitions between one state and another, and when you make transitions from one state and another, you emit light, okay? And that's the reason for this emission spectrum. Okay, so 3 key ideas in quantum mechanics. Number 1, okay, what you thought was matter is in fact waves. Number 2, matter waves can interfere with one another to produce interference patterns. Number 3, electron wave functions can tunnel through barriers. And number 4, bound electrons can only exist in discrete states, not in between. All right, intermezzo over. Now back to the Nobel Prize. Okay, and I'm going to start with something that builds on the last slide. the foundational observation that kind of started all of this attosecond business. Okay, and this foundational observation was made by one of the Nobel laureates, and Lullier. Okay, so who in a paper in 1989 said, we present experimental measurements of vacuum ultraviolet light emission, okay, in a rare gas medium, so atomic vapor, exposed to a strong laser field. Okay, so rather than an electric discharge in this tube, they just have the atomic vapor, and then they shine one of these short laser pulses on it. That's what the nature of the experiment was. Okay, apart from a small number of lines, which corresponds to discrete transitions, exactly what I was talking about on the previous slide, right? And a broad continuum, that's not interesting. We essentially observe the odd harmonics of the laser field up to very high order. Okay, that is a huge surprise. This is unexpected. We study the variation of the conversion efficiency for some of the harmonics, yada, yada. Okay, so what did the experiment look like? Totally simple kind of experiment. On this side of the experiment, they had their gas jet, okay, which they can control the gas here. And through this window comes their very strong laser pulse, okay? So they have a gas illuminated by a strong laser pulse, which gives off light. They collect the light in a spectrometer and they measure it down here. So what did they see that was so surprising? Shown here. If they just had a hot vapor that was emitting at its at the laser emission lines that I talked about on the previous slide, you would expect to see a line here, a line here, and a line here. But that's hardly even important in this spectrum. What they see instead are these other lines. And the important thing about these other lines is that they're separated by 2 times the frequency of the laser field that they used to illuminate the gas. There was no explanation for that at all when these measurements were made. This is just so strikingly not what was expected that this data made a huge splash. Okay, so and this started the whole science towards figuring out what might be going on here. Okay, so what is going on here? So, and here we come to the contribution of the Wolf Prize winner, but not Nobel laureate, Paul Corkum, whose group was responsible for providing the full quantum mechanical description of what actually is happening in order to see that harmonic spectrum emission when you illuminate a rare gas with a very strong laser pulse. And I'm going to take you through the model, which makes use of all of the concepts that I just talked about in the intermezzo. Okay, so here is a different way of looking at an atom. Okay, so the electron, which is shown here as this is this orange blob. Okay, that's an electron in an orbital. It's in a discrete state in the atom, and this thing in blue here is the potential that holds the electron to the atom. It's the potential, the electric potential that is formed by the nucleus of the atom. Okay, so you have the electron and you have the potential that binds the electron to the atom. Okay, so step 0 is to turn on the laser field. The electron wave function is bound and localized to the atom. Turn on the laser field. Okay, well, if the atomic position is where the electric field is 0, right? So what is being shown here in red is this oscillation of the electric field that I talked about before. Okay, the period of the oscillation for these kind of short laser pulses, roughly 3 femtoseconds, right? So if the atomic position is where the electric field is 0, nothing changes, right? Right? There's 0 electric field. The atom is sitting there only sort of feeling the forces inside of the atom, right? Well, what happens a quarter of a cycle later where the laser field now moves to the left 1/4 cycle. Now the atomic potential, okay, pardon me, now the potential that binds the electron to the nucleus is modified, right? You don't only have the Coulomb interaction between the electron, negatively charged, and the positively charged core. Now you have a very strong electric field also. And what that electric field does is it tilts the potential energy surface that the electron experiences and sees. No equations. I'm just telling you the facts, right? So that's what the laser field does. It tilts this potential. Okay. Well, the atomic potential gets tilted by the presence of the strong laser field. So what happens? Well, you can imagine. Here is the electron localized on top of the atom. The potential that bounds it gets bent down because of the laser pulse, right? You can get tunneling, right? Now the electron can leak out of the atom and go into a region where there is no reason for it to return to the core. This is quantum mechanics, tunneling. And important is not the whole electron comes out, right? That would be ionization, right? It's only part of the electron that comes out, right? Some of the wave function, remember, electrons are waves, they're not particles. Some of the electron wave function gets leaked out sort of away from the atom. That's what's shown here. Exactly what I was talking about before, right? So there's this potential barrier. Okay, the electron wave function was confined in here, right? But now part of the electron wave function leaks out into this other region. Okay, that's step one of the three-step model. Okay, but okay, so now you have these two parts of the same electron, right? The part that's still localized on the atom and the part that's out there somewhere, right? And the part that's out there somewhere, right, described by this leaky part of the wave function, is still experiencing the laser field, right? The laser field that pushed it away has now turned around. What was a positive laser field is now a negative. Pardon me, what was an electric field pointing in the one direction is now an electric field pointing in the other direction. And this electric field is very strong. And so it just pulls the part of the electron that had leaked out back, right? And so this part of the wave function that leaked out undergoes quantum dynamics and gets pulled back towards the atomic core. Okay, at some point, okay, it overlaps again with the atomic core. And what happens there? Quantum interference, right? This little part of the wave function that leaked out comes back, superimposed with itself, right? So the other part of itself, right? That's still localized here. And you get an interference pattern. Okay, this is step 3. Step 2 is electron acceleration. Step 3 is recollision, the process of quantum interference, and as I'll show you, radiation. Okay, so here's a little picture of a very simplified case. Okay, so the part of the wave function that leaks out is this corrugated part. The part that sort of was always localized on the nucleus is this part here. And what does this show? I hope you can see. So at one time, okay, the electron cloud is pushed over to the right-hand side, which means that you have a small, what's known as dipole moment pointing in the other direction, okay? At an incredibly small time later, because remember, these distances and times are no longer related to the light. They're related to the wavelength of the electron, right? This de Broglie wavelength of an electron, which I showed you, even for small energies, are roughly the same as the wavelength of an X-ray, right? The electron has come back and interfered with the core, which causes an interference pattern. But the interference pattern is not static, like the one I showed you before. The interference pattern is going to be jiggling. It's going to oscillate back and forth. Okay, and that interference oscillates back and forth, okay, creating a dipole that changes direction on the attosecond timescale. Okay, and that radiates electromagnetic waves. Okay, that oscillating dipole that comes from quantum mechanical interference on the atom radiates electromagnetic waves of all frequencies associated with the oscillation of the electrons because of this quantum interference. Okay, what happens? Okay, so if you only had one frequency, like I showed you on the last slide, okay, you would just see a wave that looked like this, right? But through this process of sort of tunneling and then coming back